Okay, so last time we see another proof of McFlow mean cut theorem based on LP duality, and I just kind of update the slides so that it is more completed, so you can have a look too. But the content is the same. I just make it nicer. Yeah. All right. So you will see in this class how LP is useful. So in the context of approximation algorithm. Okay. So let me just recall what is approximation algorithm. What we have is that when there is an input I, and let's say that we are considering maximization problem or minimization problem, we want to optimize something. Given input I, out of I, let's say it denotes the value of the solution from the algorithm, and let op of I be the optimal value, right? Then we say that the algorithm is alpha approximate. It's an alpha approximation algorithm if for any input, the value of this output from the algorithm or its expectation is not worse than the optimal one by more than alpha factor. So that's the meaning of approximation algorithm. Okay. So let's see some more. Like last time we saw a simple algorithm for computing vertex cover to approximation. And we will see more example of approximation algorithm today. And the first approach we're going to say is like some simple greedy algorithm, not about LP. Okay, so let's see one scenario, right? Imagine that you have a map, and you are the one who need to decide where to put a fire station into the map. And you basically you don't want to put too many fire stations because that costs a lot of money. You want to put as few as possible fire stations. But somehow, at any point of the map, it must be covered by the fire station that you put, in the sense that the fire station can reach that point within a few minutes or something like that. Okay? So this is kind of natural question, and in the sense, like you can imagine that this is kind of a covering problem. You want to put something as few as possible that cover everything. Okay? And it can happen in many other scenarios, but this problem, for example, can be abstract in this way. It's called set cover problem. So the problem is the input, you have a universe, call it E. And E has elements from E1 to En. Okay? So this universe, you can think of it as like any point in the map. Okay? And then there is a collection of set S, start from S1 to Sm. And each of the set is like a subset of the universe. And you can think of each set here as a fire station that, like, everything in this set basically cover some subset of point in the map. Okay? So, and what you want is to find the smallest set cover, T, which is a collection of sets. Okay? So what I mean by set cover, we said that a set cover is just is such that when you union all the set in T, then you get everything in the universe. It just means that every element is basically covered by some set in T. Make sense? Like you kind of want to choose a bunch of fire stations that cover every point in the map. Okay. And this problem, you can, once you get this abstract problem, you can view it as a graph problem too. How? You can say that, okay, for each element, you create a node on the right. And for each set, you create a node on the left. And let's say that I just create an edge from E1 to S1 if E1 is inside the set. And then if you create an edge like this, you get some bipartite graph. Okay. So in graph language, what you want is to pick like a subset of node on the left, right? So that every node on the right is incident to some node on the left that you picked. For example, here, if you choose your set T to be S2 and S4, this guy, then every guy on the right is incident to some color node on the left. Okay. Question about problem statement. Make sense? Okay, good. So let me ask you a quiz, a simple question. Actually, I claim that this problem actually is just really related to vertex cover that we have seen. That is, I claim that the vertex cover problem is just a problem when each element E is in at most 2 sets. That is the degree of each edge. Each element here is in at most 2 sets. So the degree of this guy is 2 at most. The degree of everyone here is 2. Okay. So you see, why is that? Like, so basically, every element here will correspond to an edge. And every set here corresponds to a node, right? And each element will be like, if an edge is an edge UV, you just create, like you are inside a node U and inside a node V. Okay? And you want to choose a smallest set of nodes so that it covers all the edges. So this is just like generalization of vertex cover. Okay. All right. But now it can be harder than vertex cover because now like this, you can have any bipartite graph here. But okay, then there is, let me try to present you one super simple heuristic to solve this vertex cover problem. Okay. It would be just greedy algorithm, where what you do is just, first you just choose a set that covers the most number of elements and add it into your collection T. And once you choose one set that covers the most element, let's say it covers this guy, then you just throw away everything that you have covered and you continue. In the next round, for example here, you can choose any set that covers the most number of remaining elements. In this case, each of the set here covers just at most 1 element. So you can choose anything. Let's say I choose this guy. Then I will just delete this guy. And in the next round, to choose a set that covers the most number of elements, the remaining guy, you need to choose S4. So that's the algorithm. And at the end, you will cover everyone. So it's clear that this algorithm gives you a set cover. Right? But you just say that it might not be optimal one, right? Because in this instance, you can choose you can choose a collection of set of size 2, like S2 and S4 would work. But this algorithm gives you like a collection of size 3. but you want to know how bad it is. Okay. Now I claim that it's not too bad. It's not gonna be like too bad. So my claim is that if, let's say, there is an optimal solution that takes k sets, then your solution T will contain at most k log n sets. Okay. So how to prove this? So suppose that I define Ni here to be a number of elements that remains after I iteration. In the beginning, N0 is just N. It's just everything, all the elements. Now the key observation is this. For every I, Ni will shrink compared to Ni minus 1 by a factor of 1 minus 1 over k. So it kind of shrink exponentially at every step. Okay. So if this is true, this looks good. But because we make a lot of progress, like the number of remaining elements shrink rapidly. But let's try to see why this is true, right? Okay. I give you like a few minutes to think about this. Maybe 2 minutes to see why this is the case. So the first thing that you should answer is, why is it the case that N1 should be less than this one? Anyone want to tell me why this is the case? At least in the first iteration? Yeah.
If you can cover it using that means, like, say there's like M initial elements. That means there has to exist at least one set that covers at least 1 over k times M of them, because that's like the best case where everything is evenly split. Otherwise, it's like imbalance, so there has to exist something that covers more than that fraction.
Yeah.
So, like, since your greedy one selects the one that covers the most, so you get that inequality.
Yeah, exactly. So you actually just answered the whole thing here, but let me just motivate, tell you to see why this is the case first, right? Well, like, you know that there exists a solution of size k, because of is k. And this solution is just a k set that cover n elements. Then there must exist some set that cover at least n over k, right? And you choose the greedy one. The greedy one chooses a set that cover the most guys. So the greedy set will cover at least n over k. So in the first round, you would cover n over k elements. So the number of remaining elements is shrink by this factor, 1 minus 1 over k. But if you think about it, the argument that I just said, it's not really specific to the first iteration at all. So just imagine that, okay, right now you have a bunch of set, and at this point of time, let's say there are a bunch of elements that you have already covered. There are n minus 1 element remaining, right? And you know that there exists an optimal solution of size k that cover everyone. In particular, it must cover everyone here. Right? So just among the optimal solution, it must cover 1 over k fraction of the remaining guy. There must be one set among the optimal solution that cover 1 over k fraction of this remaining elements. So there exists a set that cover remaining element. But, well, greedy will choose the one that cover the most remaining elements. The set that greedy choose might not be from the optimal guy, right? It might choose some guy here, but it will cover the most guy in the remaining elements, which is gonna be at least n minus 1 over k. So this just means that once the greedy one chooses some set, the number of remaining elements will shrink by this factor. Okay. Question about this? Okay, so we have this key observation. And now, given this key observation, we just say that, okay, because the number of remaining elements shrink exponentially, so in the ith iteration, the number of remaining elements is just 1 minus 1 over k to the I times n0. N0 is just n, and this thing is less than e to the minus I over k. We have seen this inequality many times. And so if I is at least k ln n, it means that ni is strictly less than 1, which means that ni need to be exactly 0, because ni is an integer, right? So you must stop after this many iterations, so the size of your collection is k ln n. So this just means what? We get that our collection T will have size ln n away factor from optimal solution. So greedy is just ln n approximation algorithm. Okay. Questions?
Yeah, so can you do an even tighter bound? So instead of doing 1 minus 1 over k, can you do 1 minus 1 over k minus I? Because there's only going to be k minus I sets remaining.
1 minus, say it again, sorry.
So
Instead of 1 minus 1 over
so
k,
it's 1 minus 1 over k minus I.
minus I. I don't see how to get this.
Because once you, like in the ith iteration, there's only k minus I like remaining sets.
No, we might not choose a set from the optimal solution.
Okay.
Yeah. Right. Okay. And yeah, like you see, that is so simple algorithm that gives some like not too bad approximation. And it turns out that it's just impossible to improve upon this. If you want like anything better than ln n, if you have it, then p is np. So it's a crazy thing, but yeah, it is true. I don't know the proof, but yeah, you can look up. Yeah. Okay, but actually this greedy is quite robust. You can try to show actually that this greedy algorithm also gives log n approximation in the weighted variant of the problem that we will see soon in this class. You can try to think about it after class. Okay. But okay, you see like you can get greedy algorithm that works and give you somewhat good approximation. Now let's look at another approach that we're gonna focus on today. How to get approximation algorithms based on a template called LP routing. Okay. So to talk about LP routing, I need to tell you first about IP or integer program. Okay. So throughout this course, when I say integer program, I just mean isn't an LP, it's just a linear program with one more constraint. That is, I need integrality constraint. So I just have a LP, but I need that my solution is integer on each entry. When this is the case, then it's called IP. And okay, without this rate constraint, the integrality constraint, you get LP, which can be solved in polynomial time. But with this integrality constraint, then IP is actually NP hard. Okay, so you cannot solve it fast. But why do we look at it? This is because IP can actually capture exactly so many problems that you will care about that you ever care about. Yeah. It just captures a lot of things very easily. And because of that, the template for LP routing is the following. Given any problem, the first step you do is just write down the IP formulation of the problem. Just translate the problem into IP, into integer program, and call it pint. Okay, you get an IP. You cannot solve it yet. So what you do, the second step is just to remove this integrality constraint, and you get an LP. This LP is just, we call it LP relaxation of the IP. So when you have an IP and you just remove this integrality constraint, you get an LP. You call that thing LP relaxation. Okay. But once you get an LP, you can solve it now. So let's just solve that. And let's say that X star is an optimal fractional solution of this LP. So it's a fractional solution, not yet like what we want. So at the last step, you need to round this fractional solution to get the integral solution, and we call it X hat for your original solution. So this is a template. You start with IP, relax, get LP, solve, get a fractional solution, then you round, you are done. Okay. So let's see how to do this in action. So first, we're going to see how to get a deterministic algorithm from this template. Okay. So the problem that we're going to look at is just the one you have seen before, vertex cover, but now let's say there is some weight as well. So you have a graph. The problem is you have a graph, right? And then there is a weight on each vertex. You want a vertex cover T, which is a set that covers every edge, right? Every edge has endpoint in the set, but you need that the total weight of the set that you choose is minimized. So this is an example of the graph, and minimum weight vertex cover would be these 3 nodes here. Okay, so that's the problem, and let's try to follow this template, right? The first step is to get an IP formulation. So let's try to do it together. Okay. So you know that the solution here is just a subset of vertex, right? So maybe the way to go is just to create let's try to create a variables, right, for each node. And we kind of want to say that this is either 0 or 1. Just to say like, for each node, you want to choose it or not. Okay. And now, because we want to minimize, so let's try to, what we want to minimize is just now the sum over all node. And you have weight. And this is just xu. Okay. So we want to minimize the total weight of the nodes that you choose. Okay. Can you tell me the constraint that we should put? Like, this is not complete yet. What should be the constraint that we should put in this thing? It should be about for every edge. Let's say for every edge UV, what is the constraint that I should write it here?
XU plus XV is no less than 1.
Yeah. XU plus XV is at least 1, right? Because this would mean that, okay, at least one of the endpoint U of V need to be chosen for every edge. And you see that this really exactly captured the problem. There's no relaxation here. It's just really the same problem as vertex cover. And so you get this thing and you just write it down. And instead of saying that x is either 1 or 0, I just put it here. It's between 0 and 1, and I just say that x is integer vector. Okay. So that's what we get. And then the next step is to relax, which you don't need to do anything. You just cross this thing out and you're done. That's the second step. And the next step, you don't need to do anything too, because we assume that we have an LP solver. So we get optimal solution, x star. Okay. But this optimal solution can be fractional. So how do we get something that like some integral solution? Let's round it. So let me tell you first how do we round as a first example, right? So I just said that, okay, for any node u, if x star u is at least half, then I just set x hat u to be 1. Otherwise, x hat u is 0. And what I return is just all the nodes, such that x hat u is 1. It means that u is chosen. Okay. So this is now some vertex set. Now, what we need to prove, there are two things, right? We need to prove that, okay, this is indeed vertex cover or not. And next, we want to say that, okay, it's not a bad solution. It's like have a good approximation ratio. So let's just do it, okay? First, I want to say that this is a vertex cover. Anyone have idea why T must be a vertex cover? Yeah.
Because XU plus XV has to be greater than equal to 1 for all edges, so one of them has to be at least 1/2.
Exactly. Yeah. Just from this constraint, this linear constraint, right? For any edge, XU plus XV is at least 1. So one of them must be at least half. So the one that is at least half, you will choose it into your set. So that edge will be covered. And this is true for every edge. So every edge is covered. And next, I want to say that T actually is a two approximation algorithm, approximate solution. So for this, let's just do it, right? Let's just calculate the size of your set T. This is just the same as sum over all nodes. This weight of the weight times x hat u. But you know that this thing is just at most 2 times x star u. Why do we get this factor of 2? Because when you round down, then x hat is even smaller than x star. But when you round up, you just round it up by a factor of 2. Right? So you get this factor 2 here. And so maybe let me write it down like this. This is 2 times this thing. But what is this thing? This is just 2 times the optimal solution of the LP. X star is the optimal solution of LP. And now, this must be at most optimal solution of the IP. Right? Because P is just a relaxation of the IP. Because you just relax some constraint. So when you relax some constraint, the optimal solution can only decrease. So this guy is at most this guy. So we just show that the weight of the set T is at most 2 times the optimal integral solution. So that's why you get T is a 2 approximate solution. Okay. Question about this? Right. So that's the first example of how to do LP routing. And let me reflect a bit on what's going on, right? What's going on is that you start with a problem that you care about, the integer problem, pint. And let's say that this is a minimization problem. Okay. And then what you do is that you relax the problem to LP. And once you relax the problem, the optimal solution can go a bit lower. And then you solve it and you get x star. And then this is just a fractional solution. Might not be correct, might not be what you want. But once I get x star, I round it up. I round this solution to x hat. Now this is the integral solution. So this solution must have value at least this guy. And what we did is that we show that the value of x hat actually is comparable to the value of x star. So what we bound is, actually we bound this thing, that the gap between value of x hat and x star is close to each other, right? Although what we want at the end is just to bound the gap between value of x and value of the optimal integral solution. But we bound something stronger. We bound this thing. Okay. And why did we do that? This is just because LP is something that we can easily reason about. Okay. So we do something stronger than what we need, but that's what we do. Okay, so let's see more example how to do LP routing. And now it's going to be the randomized one. Okay. So the problem, just so that you are familiar with, to make it easy for you, let's look at similar problem that we have seen, set cover, but now it's weighted one. So it's just the same problem. You have universe, you have a set, a bunch of sets, but now each of the set have cost. There is a cost on each set. And what I want is to find a set cover T such that it has a minimum cost, minimum total cost. Okay. So that's the problem. And let's just see how to use this template again, right? Okay, so what should be the variable that I create? Can you tell me? Yeah.
It's like the same indicators for each thing in S.
Yeah, because what the solution is like a subset of a set of S, right? So what we do is just for every set in S, you create XS, indicating whether you choose S or not. And what's about the objective? What should be the objective? Yeah.
Try to minimize the cost of the set.
Mhm.
So it'd be like the sum of the C of S times XS.
Yeah, exactly. Summing over all S. All S in S. Yeah. So this is really like the total cost of everything that you choose. Right? And what about the constraint? What should be the constraint?
For everything in your universe, the sum of all XS that contain it, the addition of all of those greater than or equal to 1.
Yeah. So what we say is, so this the constraint is that it need to be the set cover, right? So every element must be covered. So we just create. First, you just think like what is the constraint? So you just say, okay, the constraint for each what? It's just a constraint for each element. So maybe just start with this. And then you ask yourself, what is the constraint for each element E? Well, you need to cover it at least once. So because now X is either 0 or 1, all you need to do is just to put the sum of our S for our set that contains an element. You need to be at least 1. Okay. This means that like some set that contains E must be set to 1. So there. So now you get an IP. So you get this IP. And now the same thing, right? Relax, solve, and then the next thing is to round. So you see the creative part that you need to work is really like kind of the first step to model the problem to be IP. And then you just relax and solve. And then you need to think, how do you round this thing? That's the two things that need some creativity. Okay, now if I tell you that I want to round this thing using some randomization, what do you think should be the most natural way to round this with randomization? Any guess? Like at this point, it's like not that clear, but just a guess.
Maybe pick a random threshold, and then everything above you include, everything below exclude.
Actually, that might work. One sec. Oh, no. Oh, wait. I'm not sure. I don't think it works, but I'm not sure. Yeah. But yeah, very natural way to think. But let me at least tell you the solution that I have, right? I just do it independently for each set S. So you think like, you should think of X star S. Think of it as a hint, right, on how much you should choose the set S. Because LP kind of solve it for you, and it gives you some fractional value for each set. And this thing is just something between 0 and 1. If it is so close to 1, then you should choose it. If it's so close to 0, maybe you shouldn't choose it. So what I do is just, if it's close to 1, then I set it to 1 with the probability, which is just XS star. Otherwise, I just set it to 0. Okay. And then once you round this thing, then there is a natural way to define your set, which is anything that you set to 1, you just put it into your collection. And so now you have this. Let's try to analyze it. Right? So it will not work just yet, but you will see why it doesn't work. Okay. Let's analyze. First, we need to compute the cost of your set that you choose. And the expected cost is just, this is not, it need to be expected cost, right? Because your set is randomized. And the expected cost is just total cost in T, which is by linearity of expectation, this thing is just a sum over all set, right? CS times X hat S. So by linearity of expectation, you put the expectation here, right? And expectation of X hat S is just X star S. Because you choose X hat X to be 1 with this probability. Now, what is this? This is again just the optimal solution of the LP, the optimal value of the LP, which is at most the optimal value of the IP. Okay. So what do we get? We get that, at least in expectation, the cost of your set is actually optimal, right? It's as good as the optimal one. Okay, so maybe things look too good to be true. But yeah, it is indeed the case because if you now let's try to analyze that T is a feasible solution. That is, T is indeed a set cover or not. Right? We need to analyze this too, not just the cost. Okay. And what we get is that I want to show that for each element, it should be covered with high probability. But what we can show is only that, let's analyze the probability, let's bound the probability that each element is not covered. The probability that E is not covered is going to be the product over our set that contains E, 1 minus X star S, right? Because that's the probability that none of this set is chosen. And then what is this? This is just algebraic manipulation. Now you just replace this by E to the minus XS star. So you get E to the minus sum of this thing. But you want this thing to be so small, but all you can say is that, well, this sum here is at least 1, just at least 1, right? So this is just kind of at most 1 over e. Why this is at least 1? Just follow from your linear program, right? Because x star is a linear program solution, so it must satisfy this constraint. Okay, so we want to show that this probability is so small on every element, but we just get this kind of weak bound. Each element is not covered with some, like it's at the probability that you don't cover some element is at most like at most half. Okay. So this is something, but it's not too strong. It's not strong enough, right? Maybe like with this bound, maybe some element might not be covered. So you see, this is why things that looks too good to be true, like why don't you like just solve this problem exactly and prove that P is NP? Yeah. Okay. Okay, so this set T is not feasible, not yet. But let me ask you, can you try to fix this algorithm? There is a way to boost this probability so that this is so small. How do you fix this algorithm?
Run at 1,000 log n times.
Yeah. So we have seen many times in our course how to boost probability from constant to be like polynomially small. Just make copies, right? Okay, that's a quick fix. Just generate k which is log n copies of everything. Just generate like a t1 up to tk, like we did. And what you return is like the union of this guy. So the cost, the expected cost will increase by a factor of k, which is log n times opt. But now the probability that some element is not covered by t means this can happen only this element e is not covered by any ti, which means that like there are k of them, so it's not covered by any k set here, and each of the set doesn't cover e with 1 over e probability. So that's like k is log n, so this is like very small. And then by union bound, you get that every element e must be covered by a set T, by this collection T with high probability. Okay, so that's a quick fix, and yeah, easy. So what do we get now? We get that T is a log n approximate solution with high probability. Okay, but note that this bound is just within expectation, right? We get this with just expectation. Can you fix this again to make it with high probability? Okay.
Make a bunch of independent copies, take the median of means.
Yeah, that would work. Yeah. So make even independent copies, take median of means, that would work. But yeah, let's say that this is like 10 log n, right? You can also do it from scratch again. Say that, okay, the probability that, let's say this is, what I mean is, if the expectation is 10 log n, then the probability that this cost is more than 20 log n, this is going to be log n opt. This is going to be at most half, just by Markov. right? And yeah, because now you get that it will not be more than 20 log n by Markov with like a with probability half. Now you make log n copies and take the minimum one. Then you make it work with high probability now. Okay. All right. Good. Question about this? All right. So let's see more like a bit more advanced example. I want you to see like some nice problem which is called congestion minimization. So in this problem, it's a problem where you have a graph. Okay, you have a graph, and then you have pairs of nodes S1, T1, S2, T2, and K pairs of them. And what you need to do is to find a path from S1 to T1 and from S2 to T2. Okay. Just return K path. But what you need is that you need to minimize the congestion of this path. What I mean is that, let's say that the congestion of an HE is just the number of times that this HE is used by the path here. And what I want is that I want that every edge has small congestion. We want to minimize the maximum congestion on each edge. And this is the problem that people need to solve in real life, actually, when people need to like design some electronic circuit. It's like there is some demand S1 to T1, which need to be routed somehow, and S2 to T2 need to be routed somehow. And what you need is that like there's at every place the capacity of like the Y in the circuit should be small. Okay. But you can, for us, we can think of it abstractly like a graph. Yeah. Now this is less trivial. Okay. Let's try to do this template, right? Get an IP for this problem. Okay. So what I will do, let me denote Pi as a set of all Si to Ti paths. And suppose that I define this for every path in Pi for all I from 1 to k. Okay. I create a variable for every path to choose it or not. Okay. So now what I need is that for every I, right, I want to choose one path. So here I say that for every I need to choose one path that connect Si to Ti. Okay. Now, how do you capture this thing? Optimizing for the congestion. So suppose that I know that it's need to be minimization problem, right? So let's say that I want to minimize something, and then I know that the constraint must be on every edge. Okay, now the big question is what do we write here? Yeah.
Is it gonna be like the sum of the
Which one do you talk about? This one or this one? The constraint.
yeah, the constraint
The sum
of all the paths that contain E should be at least one.
At least one. This means this is not right yet, because this means that you want every edge to be used at least once. But what you want is you want every edge to be used not too much. So maybe we want this to be upper bound. Right? Okay, you are in the right track. Maybe what's next? What I should put here and here. By the way, nothing stops you from putting this as a variable. Even if this thing is a variable, it's still linear constraint.
Just put it under there.
Exactly. So, okay, if I put a dummy variables here, let's say C for congestion, then what else?
C.
Exactly. Right? So I want to minimize the congestion, and this should be the upper bound for every edge. So here you just say that every edge is used by at most C times. And we want to minimize this thing. And this can be a variable. That's the point. You don't need it to put it to be some fixed constant. Okay. So, okay. Good. Yeah, in your homework, you will see how to, you will practice how to come up with IP for a lot of problems. Okay, so now you get this, and I just rewrite it. Instead of 1 or 0, I just put this linear constraint and say that this is we put integrality constraint there. Okay, so we get an IP. So now the second step is to relax. Easy again. And okay, the next step is to solve. You get an LP. This is an LP, but can we solve it? Because this is an LP of exponential size, right? The number of variables here correspond to each path from S1 to Si to Ti. There are exponentially many paths here. So this LP actually, if you want to solve it, it's not good. It's just the size is just too big. Cannot be solved in polynomial time. But the thing is that this is a special LP that you can actually solve it in polynomial time. So why is that? This is when the intuition about flow that you have learned is useful. So let me tell you that I claim that if you look at this LP, instead of solving this guy, you can solve another LP here instead. So let me read this LP to you, right? So Okay, before going there, you should think of this problem as you try to send 1 unit of flow from S1 to T1 and do this for every pairs, such that the capacity of every edge is bounded by C. Right? So now, once you think of this as a flow problem, you can say that, okay, what I can just write this instead. I kind of create FIE, a variable, for for each edge, and I. Okay? This is kind of the flow for I pair on HE. And what I need is I need to send one amount of flow from SI. I need the flow out of the source, the I source, need to be 1. And then the flow, I have flow conservation on every node, which is not SI and TI. Okay. So given this thing, it means what? It means that FI will be sending 1 unit of flow from SI to TI. Because it go out from S by 1 unit. So it must go into T by 1 unit. Okay. And now you have that, what you need is that for every edge, the sum, the flow overall pairs, there are a K kind of flow here, right? Not just one kind of flow. Sum over all I from 1 to K, Fi of E is at most C. Okay. So and now what we want to minimize is the capacity here, the C. So you see this LP is a kind of K commodity flow problem. You have K kind of flow. For each kind, you want to send from for the ith kind, you want to send from SI to TI by 1 unit. But for every edge, the total flow over all K kinds is at most C. Make sense? This interpretation? Okay. And now, my claim is that once you solve, and this you see, this is an LP with just polynomial size. There are number of variables here, and constraint is just polynomially many. So you can solve this LP. Okay, but I claim that once you solve this LP, you can actually extract your solution from this LP to this one. And how? We will use flow path decomposition. Given flow here, you can extract and get a path here. How exactly? Well, this is really already in your homework, the flow path decomposition algorithm. So in the homework 5, there is a problem called flow path decomposition. Use that idea to get the solution from here and give the solution here. Okay. So my point, that's not the big point of this lecture here. The point is that I claim that, okay, even though this LP looks big, you can solve it in polynomial time. Okay. And you can just solve the LP P prime that we have seen instead. After you solve P prime, you extract the optimal solution for X star for this LP, and you get the optimal solution for this LP. Okay. Anyway, now we solve and get X star. Next question is, how do we round? Okay. Any suggestion? Yeah.
The probability thing and then make copies like before, or would that not work?
Yeah, so you said that maybe think of XP as the suggestion on like whether we should choose the path P or not, right? Yeah, that's a good idea. So let's say that. So one natural idea, right, is just that okay. Just choose P with probability XP. Okay. And if this is the case, then you can actually see that, like at least in expectation, the congestion should look good, right? The number of times that you choose a path that goes through an HE will be like the sum of XP because you choose each path with probability XP. So in expectation, from here, you have that the congestion, the expectation of the congestion on E will be just the sum of P containing E of X star. Okay. Which is at most C. So the expectation looks good. But there is one problem though, that is, it's not clear that if you just look at each path P and choose it with this probability XP star, it's not clear that this solution will be the case that it will connect every pair, right? You might have some pair, S1, P1, and there is some path. Let's say this path is like a probability 0.1, this path is probably 0.9. It might be the case that you just toss a coin on each path here, and you just don't pick any of them. That's possible. Okay. So what we need to make sure is that you really need to, for each pair SITI, you need to pick one path for sure. At the same time, you kind of want this in expectation, the congestion should be still small, comparable to X star. So now let me just tell you how to do this. What I will do is just that for each I just say that I pick one path for sure. I just pick one path, P hat I from Pi, and I pick one path with this probability X star P hat I. Okay. And why this makes sense? This is because if you look at this collection of all paths from Pi, this collection of X star P for all paths P in Pi, you can think of this as this probability distribution, right? Because every guy here, every P, X star P is the number from 0 to 1, and the sum is 1. When you have a collection of number between 0 and 1 and its sum is 1, you can think of it as a distribution, right? And I just choose one, like now this is a distribution over all paths from Si to Di. So I just choose one path, and with according to this distribution. Okay. Does this routing scheme make sense? At least what I do. The statement should like, okay. It's not clear why it works yet, but the statement how to do this is clear. Okay. And once I do this, I know that for every pair, I get some path now. So it's a feasible solution that connects Si to Ti for every I. Now it remains to bound the congestion. All right. So what we will do is to use Chernoff bound, the one that we have seen before. And okay, let's analyze it. Okay. So suppose that I let YE be the congestion of E. That is just count the number of I such that E is in the path P hat I that I choose. And we want to bound the maximum congestion over all H. So to use Chernoff bound, right, I need to kind of say that YE is a sum of independent random variables. That's only when Chernoff bound kicks in. If you cannot do that, then you cannot use Chernoff bound. So I want to say that YE is a sum of some independent random variable. So how do I do that? I just create a random variable XEI. This indicates whether E is in the ith path that I choose. And now you see that for each different I, XEI are independent. Because for every pair, I just choose each pair here independently. Okay. So this guy are independent thing. Okay. And now, so now like this is YE is something that we can use Chernoff bound. So before we use Chernoff bound, we just need to bound the expectation. Okay. And the expectation of YE, right, is what? It's just sum over all path that contains E, right? And it's the expectation of the indicator whether E is in this path or not. In the I should sum over all. Yeah. Maybe I do this. Sum over all I. Yeah. And then for all P that connects Si to Ti, only the guys that contains E, the probability that E is in P. Right? So this is just X star P. And this is just the same thing as, maybe do you understand this? Like this is just like expectation of the indicator, right? That E is in P. But we choose P with and that this is just probably that. Yeah. This is just X star P. So this is just sum over all paths. containing E. But this is at most C, which is the opt of the LP. Okay. So you have that the bound in expectation. This is at most opt of LP. And now we can say that okay, you get some expectation, which is kind of in expectation is optimal, is at most like opt of LP. And when you try say that you want to use Chernoff bound, normally like when you just say that okay, any random variable when it is a sum of independent thing, it shouldn't be more than its expectation by log n. This should happen with high probability from Chernoff. That's like how like the rule of thumb, right? Like you can do it using some math and like just apply Chernoff and you get this, and it is like. It is more like y is more than expectation by like a log n factor. That can happen with very small probability. So I will skip this. It's just calculation. You can verify it. But what you get is that then you get that ye is at most log n factor times max of 1 and opt LP with high probability. And so, but 1 is always the lower bound of the integral solution. Opt of LP is the lower bound of integral solution too. So both of this is at most opt of IP. So for every edge, you will use the congestion at most like log n away from the optimal thing. So you get log n approximation algorithm. Okay. So you can get a bit better than even better than log n, much better than log n, if you know that opt of LP is actually like at least log n, because then like Chernoff bound concentrate even more. Okay. You can check that just for your understanding that if opt of LP is big, then you can actually get 1 plus epsilon approximate solution. Okay, just from the same algorithm. Okay, let me wrap up. So what we see today is we saw 2 strategies for designing approximate algorithm. One is greedy, kind of ad hoc, but it's very simple. And one is super generic way to get the approximation algorithm. It's called LP routing. Just start with IP, relax to LP, solve it, and route it. Okay, it's very generic. And if you want to learn more about approximation algorithm, I recommend this textbook. It's great. Okay. And tomorrow, next time we're gonna learn, I think, a bit more about approximation algorithm and its relation to LP. Okay, yeah, see you next time.